let's look at question, not 11, 9. Question 9. So, I'll come back to this slide in a second. Am I videoing? Yeah. All right, so think, and if you have your foldable in front of you, that's great. Think about what we're doing in A. We're taking an element and another element, and we're putting it together. Of our 5 types of reactions, which is that? Synthesis, because that's which type of the synthesis is it? Binary synthesis, because we have, you might even put binary next to that to further help classify it in your head. Remember, like when we did nomenclature, we identified, oh, it was ionic, acidic, or covalent, and then our brain automatically picks up, oh, it's covalent, I did this. Think it's ionic, I do this. So it helps if you categorize things in your head that way. All right, so it's binary synthesis. B, we see a hydrocarbon reacting with O2. I told you yesterday the reactant O2 is going to be an obvious choice for which type? Combustion, yes. And if you have O2 as a reactant, you have to label it combustion. Occasionally we'll have one where we will put it as synthesis, but it also depends on the style of combustion. Well, this is not synthesis combustion. This is like straight up, boom, pow, we got some fire going on. Combustion. This is like hexane or octane combustion in a gasoline engine. So that is combustion, which makes the carbon dioxide and water products. If I were to balance that, which you are in this case, what did I tell you to start with yesterday? Balancing which one first? Well, I told you for combustion, it's kind of nice to balance in one way. CHO? I told you that? CHO? May have been doing that in my first period, my bad. When you're balancing combustion, so let's balance this one now. C6H14. Plus O2 yields CO2 plus water. I would balance my carbons first. So how many carbons do I have over here? 6 over here. So what do I need? 6 coefficient on the carbon dioxide. How many? So now I'm going to show CHO. So I've got my carbons taken care of. Now I'm going to do my hydrogens. How many hydrogens over here? 14. I need 2. So I have 2. So I need a 7 here to multiply out. So that gives me 14 hydrogens. And then oxygens are last. And I save oxygens for last because they're in like 3 places. And sometimes, you know, they kind of self-balances out before you even have to attempt it yourself. So I see 2 oxygens over here, and total over here, how many? 3.
No, you got 12, 19.
19. How do I get 19 equal 2? I can't, right? Okay, so I have to, so if I wanted to, I can't, but if I wanted to, I could put 19 halves here, and that would give me 19 total, because 19 halves times 2 is 19. But because I can't put a coefficient that's a fraction, I'm actually going to go through and double everything, which is what the 2 in the front here was what you were saying, Austin. So this would be what?
19.
And this would be 12. And this would be, 14. And yes, B and F are the same. My bad. Exactly the same, without a doubt. Okay, so that's AB. Then I'll put hydrocarbon here if you're trying to categorize your types of reactions. C, we have element plus element. They are diatomic, but they're just simple elements, makes one compound. Binary synthesis, and I'm just going to put synthesis, and then next to it put binary if you need to help classify that further. Yeah.
Does it matter that they're both non-metals?
It doesn't, actually. Many times binary synthesis will make something ionic, which is a metal and a non-metal, but simply taking, and so, of course, I take every reaction and put it in a nutshell. So occasionally with a crack nutshell and go outside, and you look at some exceptions to our generalizations, but the generalizations help you kind of understand the basic first before you start diving outside. But yeah, this is still binary, despite it not being ionic, okay? So D, we have a singular element, so a metal, plus water making what? A metal hydroxide. And hydrogen. So it's hard to see what's happening here. But I told you guys yesterday, occasionally you might want to write water how? HOH. So if you write HOH, sorry, I'm using this board instead of that board, but erase. So lithium plus HOH, what happened? Lithium switched places with who? Hydrogen. You switch with hydrogen, lithium gets the hydroxide, right? And hydrogen got booted out, but it can't be just H. It had to been diatomic. So what kind of reaction is that? Yeah, single replacement. Okay, so that's single replacement. Next one thing broken into many. Yeah.
I have a question. question about these. So since you're just balancing out and like H2 is like it stands for 1, does that mean that there's still only 2 hydrogens or is there 3 bonds?
So to balance, basically going to balance this, right? If you write it as HOH, it's so much easier to balance. I think of hydroxide.
On the other side.
I know, but if I go with the whole flow, it'll work out. So think of it as HOH. OH and OH, I have 1 of each, right? But the H2, I got 2 H's over here, but 1 singular H over here. So I need to put a 2 in front of this whole thing, right? So that gives me 2 of the H's, 2 of the H's. But then I also have 2 hydroxides, right? So how do I make 2 hydroxides over here? 2 in front of the lithium hydroxide, and I gotta put 2 in front of the lithium over here. And so you have to go through the whole shebang. Okay. What's the next one? Oh, one thing into many. Decomposition. You just know the style of that. Now this isn't any particular decomposition because it's not one particular that we learned, but you can still recognize it as decom. F we already did. G. Decomposition again because it's what? One thing into many. Even though it's not one of our 4 styles of decomp, you can still recognize it because it's 1 into many. Barium oxide plus water. Barium oxide plus water makes barium hydroxide. Which type of synthesis? This one happens to be a metal oxide synthesis. So this is synthesis, and the metal oxide plus water makes metal hydroxide style that we did talk about for a couple days now. Next one. Say again. Pretty easy to see that one. I think those are the easiest to see out of all of them because it's two things, switch to the partners, move on, and it's balanced in this case as well already. Calcium chloride calcium chlorate makes calcium chloride plus oxygen. Which style of decomp? Metal chlorates. Yeah, chlorates make a gas, not chlorine gas because that would kill us all. We make chlorine, or we make oxygen gas, which is a friendly gas. Next one. Double. You see the 2 partners. You see the 2 partners. You see them switch. And then next, this is an interesting one. Why?
The O2.
Yep, I told you the presence of oxygen as a reactant meant it was combustion. Most commonly, occasionally, if we have a singular metal here plus oxygen, we would call it binary synthesis.
So if it has oxygen in the reactants, it's definitely combustion.
If that's an option, yeah, I would label it definitely as say again. O, M, L. L, nope.
Single.
No. So we just said this all out, and I only said this one more time. So the presence of what?
Oxygen.
So that's your key sign right there. The presence of oxygen meant it was combustion, as we spoke of yesterday. Okay, then rubidium plus, what is HC2H3O2? What is that guy?
Acetate.
That's acetate, C2H3O2, but it's
Acetic acid.
acetic acid. So that is an acid because it's got H in the front, so it's acetate, acetic acid. So rubidium's replacing what? The H, they switch places. Okay, just a 1 single replacement. Yep, so that's single replacement. So the rubidium gets with acetate and hydrogen gas becomes diatomic. All right, so you should be getting comfortable, like at least recognizing the style of reactions. And I've given you all these products. On 12, you're predicting your own products. And how are you going to do this on 12? Well, these are all your reactants, right? Follow the what? Reading at 11 probably gives you a lot of information, but you guys have your notes with your how does synthesis look, how do I predict, how does decomposition look, how do I predict. So you have your prediction patterns. You need to use your notes really extensively here. And reading at 11 probably has some help as well. Okay, so this is due tomorrow, and if you haven't started, I hope that you got some homework tonight because I know this is one I gave it over the course of 3 days, so you didn't have to do it all in one night. But you do what you got to do. Okay, so let's chat about this before we move on to our lab. This is all really relevant to what the heck is actually happening in a reaction, okay? So, some of the evidences of chemical changes we already spoke of. Jonathan, tell me one. One evidence of chemical change. Gas evolution, right? So we can see gases, and that's many times what's happening in combustion reaction. Rashida, tell me another. Precipitate. Many times we see precipitates in double replacement. That's how we know reaction's happening. Chris, give me one more. Well, what do you see with combustion? How do you know a chemical reaction is happening? Heat, fire, flame, light, things like that. So obviously those are like there's a reaction happening, you see the changes. What if I put a liquid into another liquid and it just looks like a liquid?
That's not good, you gotta.
Well, do you know a reaction happened?
Oh no.
No, it probably didn't happen because unless you can see some of the chemical evidences of change, you may not really think a reaction happening. So this is how we prove a reaction is going to happen or not going to happen. And then on top of that, we're like, what actually is in the reaction that's actually doing the reaction to make it happen? So what we do is, I'm going to make an analogy before I move on to we had a game last night, baseball and softball, and I don't know if anybody else. Yeah. Okay. Who played or went to a game last night? Okay. Who was in theater? Are people watching in theater yet? Okay, so you guys have audience members in the crowd, right? What do they do in the game? They spectate. So they play in the game? No, they watch. So they don't do crap, basically, what you're saying, right? They're just there. They're warm bodies. They cheer us on and make the reaction happen faster. Maybe they're there to watch. That's what their job is. That's why a couple of times in a reaction, we have 2 or more ions that are spectator ions. They don't do crap. They're just there. They help the reaction along in terms of getting things together, but they don't do anything. So we actually recognize that and we say, you're not really important. The things that are important are the game players, the ones that are making something happen. So we're going to utilize these rules as we go through an example. I'm going to play this video first, and I'm going to write it on the board as we go. So write it down with me, because hold on. I like to make sure that my music is off. Okay, so here we go.
And now we can use it to do stoichiometry, for example, and to make measurements. But now let's go to an aqueous reaction. And so in this reaction, we're taking lead nitrate, which is clear, and we're adding it to a solution of potassium iodide, and it produces a yellow precipitate. And so what we're getting is a solid that comes out of it. And so I could observe that. I could know what those chemicals are.
Okay, so he says lead nitrate. He means lead 2 nitrate. And then with lead 2 nitrate, he's adding potassium iodide. What are your reactions or reactants? Are you writing down the reactants as we go? What's the first one?
Lead nitrate.
Yeah. Formula. PbNO3 2. You're writing this down with me. So I'm going into like 2 really healthy examples. Okay. PbNO3 2. That's lead 2 nitrate. Potassium iodide. Just Ki, because potassium's in group 1, iodine's in group 7, so potassium gets a plus 1, iodine gets a minus 1. Okay, so just that's all related back to electron configurations. All right, so you guys tell me, what kind of reaction is this? This is a chemical reaction. Give me what kind of reaction of the 5 types?
Would it be double?
Say again?
Double.
Has to be double. Why double?
Because there's like
2 ions.
each.
Yeah. 2 ions and 2 ions. If you have 2 ions and 2 ions, they basically change partners. So lead's going to get with who? Iodine, the other anion. Okay, so that makes lead. Come on, guys. Lead I2. Why I2?
Because lead has to crisscross the 2.
Right, lead has a 2 charge, iodine has a 1, crisscross them out, okay? So then that's lead 2 iodide, and then nitrate and potassium are the only ones remaining. So if nitrate or potassium is a positive charge and nitrate's a negative, they get together to make what? Potassium nitrate formula. So what's potassium? So you guys shouldn't be asking me, is it this? What's potassium's charge?
Plus 1.
Plus 1. What's nitrate's charge?
Minus 1.
Minus 1. It's in your head. Crisscross, you're done. Okay, so is this balanced? No. No. So balance it out. What am I adding where? 2 in front of potassium, what? Iodide and
2 in front of potassium.
2 in front of potassium nitrate. Okay. So far so good. We know how to do double replacements. On your sheet of paper that you wrote down your warm-up information on, it probably says balanced chemical equation, but maybe not. First up is to what? Determine solubility. You guys got the blue sheets in front of you? Look at the solubility rules. What does the solubility rule say about nitrates? They're soluble. Always, right? No matter what it's paired with. So nitrate right here, put a little AQ behind the 2. That means aqueous, potassium, or lead 2 nitrate. And then again, potassium and nitrate, this also will be what? Aqueous, right. So those AQs mean aqueous. What the heck does aqueous mean? Just dissolves in water, soluble, will ions, and so forth. Alright, what about iodides? Okay, so iodines are soluble except in what?
Silver, lead, and mercury.
With silver, lead, and mercury. So what about potassium iodide? It's fine, it's soluble, it is insoluble category. Then we have this exception over here of lead. So how do I label this? Either a solid, or I can put a down arrow, or I can put PPT. Any of those will work. I'm just going to put down arrow for that sake. All right, so the balanced chemical equation's done. We've done the solubility. What's next? Okay, so which ones am I ionizing? All the ones that are aqueous. So when I say ionize, that means we're actually going to break the 2 ions that went together back apart. That's all we're doing. We're basically saying it went in as lead 2 nitrate, but truly it's lead 2 plus and nitrate 1 minus. That's actually what exists in the solution. But we have to quantify, like there's 2 nitrates and so forth. Same thing here, this will break apart. Does this break apart? No, keep it together, don't touch that. No. Okay, and then break this one apart. Okay, so we're going to go through and break this part now. No marker. We'll go this one. Okay, so lead gets back its charge, and that's going to be lead 2 plus. How many nitrates do I have? 2. So I'm going to put plus 2 nitrate ions. So basically I'm just taking it and ripping it back apart. Okay? And then how about this one? And yes, so this 2 distributes to both of them. The coefficients do apply. That's 2 K charge, 1 plus, and then 2 I 1 minuses. Okay? So far, everything aqueous has dissolved. We're showing it ionizing. What about this one? Leave it exactly as it is. Can you guys see this blue okay?
Yeah.
In the back? Just making sure this blue is about the back. So PbI2 precipitate. Leave it alone, don't touch it. Exactly as it's written. How do I handle this one?
2 potassium.
2K what?
1 plus.
1 plus, because it is a charged ion, and
Plus 2 NO3.
yes, there's 2 distributes to potassium and to nitrate. So there's 2 NO3, 1 minus charges. Okay, so at this point, we took our molecular equation, which is up here in purple. This is what we're used to. We ionized it into the ionic equation, which is just like ion, precipitate, ion. Then we have to look for what's to say next.
Cancel the spectator ion.
Cancel out the spectator ions. And what is a spectator ion, Megan?
It's the ones that aren't used in the net ionic equation.
Okay, because they are what? They're what?
Exactly the one.
Okay, so they actually didn't react. They're the spectators, just like a fan. They come in, they watch the game, they leave. They're actually not doing anything. So who is not actually making a chemical change happen?
2 potassium.
2 potassiums, big chillin right here, and right here. They're not doing anything. Cancel them out. They're just there to help the process occur, but they're not reacting to form a precipitate. Who else?
Nitrate.
2 nitrates, and that's it. 2 NO3 1 minus. They have to be exactly the same. 2 NO3 1 minus. So if one of them has a charge and the other one doesn't, I wouldn't consider them the same because they actually are different. So in this case, they're the same. We cancel them out. So who's the game players? Who are the participants in the precipitate? Lead 2 plus and 2 iodines. So we're taking this one, and we're making what? Lead 2 iodide. Precipitate out. There you go. So what we have here in purple is called the molecular equation. What we have here in blue with all the cancellations is like just the ionic, that's the working part. And then this is our final answer. We call this the NIE, net ionic equation, because net means total after consideration of the spectators. All right, so let that sink in. He's going to walk through the process. He's going to explain and show some more pictures with it. I think it's helpful to see it a second time.
Chemicals are, and then I'm going to write it out. So we've got a solution of lead nitrate, solution of potassium iodide, and it's making a yellow precipitate of lead iodide. It settles to the bottom. Next thing I want to do is I want to write out my reactants and products. Now, if you don't know how to go from the name of a chemical to its equation and vice versa, I'll put a link down here to a naming molecules or a naming compounds video that should help out. So the first thing I want to do is I want to write out all the reactants and products. And now we've got lead nitrate, potassium iodide, making lead iodide, and potassium nitrate. Next thing I want to do is I want to make sure that I balance it. And so I can see right here that I don't have enough iodine on the left side, so I could add a 2 there. Now I've got too many nitrates on the left side, so now I can balance it like that. I also have to write the state that it's in. So remember, those first two were aqueous, but this lead iodide is going to be a solid. And now I've got a nice molecular equation. But again, this video is about two other equations. We've got ionic equations and then net ionic. And so how does that work? What is an ionic equation? Well, if you think about this lead nitrate right up here, it's not sitting in that solution as a connected molecule. Remember, it's going to break apart into its ions. It's going to have its lead ions and nitrate ions, and those are going to disassociate from one another. Those are going to separate from one another. And so when I'm writing out an ionic equation, what I have to do is I have to write out all the ions. And so let's do that one first. I'm going to have that lead ion, which has a 2+ charge, and then 2 of those nitrates, which have a 1- charge. Now, why am I writing a 2 here? Because we have 2 of those nitrates. And so you can see in an ionic equation, what I'm doing is I'm busting apart each of those ions. Let's go to the next one. So that potassium iodide, I'm going to break that apart into its 2 ions as well. You can see that I'm writing that this is in solution, so it's aqueous. Next, we get to the lead iodide. Now, remember that lead iodide is a solid. It's that yellow solid. And so I'm not going to bust that apart into its ions. I'm just going to write that as lead iodide as a solid. But then this potassium nitrate is going to break apart into its different ions, so I'm going to write it out like that. So I know that's a lot of work, but this is a complete ionic equation. Why is that important? It really allows us to look at what ions are in that reaction. So if it's ever an aqueous reaction, lots of times we'll use this ionic equation. Sometimes I'll call it a complete ionic equation because it's showing all of the ions that we have present. Okay, what's the third type of equation? That's going to be the net ionic equation. So if we look back at this equation, you can see that we have 2 nitrate ions on the left side, and we also have 2 nitrate ions on the right side. And so they're really not being changed in this reaction. And so we call those spectator ions. They're really just watching. And so what you can do is you can cross out things on the left side that are also found on the right side, as long as they're in the exact same form. Can you find something else on the left side that's also on the right side?
Can you?
That's going to be those potassium ions. So I can cross those out as well. And so once I've crossed out all those spectator ions, I can write it out like this, and that's going to be my net ionic equation. So that's really, it's just showing what atoms are part of this chemical reaction that are actually forming these bonds. And this will become important when we're looking at redox reactions in the front. So now, once you've got those equations, so this would be a molecular look-like.
Okay. So I want you to at least see the particulate nature of these, because this refers back to the bonding stuff a little bit. Looking at this blue thing with 3 red things on it, what ion do you think that's representing? Why nitrate?
It's
NO3, right? So who do you think this little gray one is? Lead. So why are there 2 of these? Because there's 2 nitrates. Beautiful. Keep going.
Solution, remember, they're not connected. They're dissolved in the water.
So
Next, we're going to have the potassium and the iodine. So those are going to be separated as well. This is going to be the iodine, or the big purple spheres, and the small purple spheres are going to be the potassium. And now we're going to have a reaction. What does it look like after that? Then we're going to have the nitrate and the potassium ions. Again, those are spectator. They didn't change. Then we've got the lead iodide. You can see that's that yellow.
So this right here, this purple and gray thing, what's it trying to show you? But how is it showing you solid? It's all smushed together like a, say again? Lattice, somebody said it. So like a lattice structure, and that's supposed to be indicating that to you. So if I give you pictures like this, don't feel afraid. Like, be comfortable with this, especially if I label them. And you can see the nitrates didn't do anything. They just stayed hanging out like normal. And so did the potassiums. Okay, so let's do one more like this, but I want to give you guys a chance to try it yourself. So after that, we're going to do our lab. I keep going to the wrong side. So go finish this up for me. Magnesium chloride and sodium phosphate. Walk through all your steps just like you did. I like to try to do a sample and then let you try using your own notes so that you have that reference to go. Yeah, do your reaction, go through the process that we just went through. Yeah.
Salt.